Pradhan Research Group at Jackson State University. So today I'll be talking about high broadband photoconductivity of few-layer MOS2 phototransistor measured in multi-terminal method and effect of contact resistance. So before going into the actual work, first I would like to introduce the 2D materials and its applications. So 2D materials is a kind of layered materials that are crystalline in nature, and nowadays these materials has gained a lot of attention due to its very single to very few atomic layer thickness and good optoelectronic properties compared to its bulk and other properties like transparency and flexibility. So here you can see the layer structure of graphite, which is an allotrope of carbon, and this is actually consists of stacks of graphene, where graphene is a one atomic layer 2D hexagonal lattice. In the below left side, you can see another 2D materials that is named as transition metal chalcogenide. This is kind of different from graphene, and this is a kind of MX2 type 2D layer materials, where a layer of metals is sandwiched between two layers of X halogens. So these materials are nowadays at forefront because of its significant band gap, and this band gap is tunable in UV visible region. And also you can see the layer structure of black phosphorus and boron nitride here. So in this slide, you can see how we are making these 2D materials in a lab. So you can get these materials by mechanical exfoliation technique. So for that, you need an scotch tape and a very tiny amount of this bulk crystal. So by doing mechanical exfoliation from layer to layer, you can finally get the single atomic layer. And after transferring these materials to the silicon dioxide substrate, you can see those materials under optical microscope, and also you can measure the thickness of this single layer to few atomic layer materials by using atomic force microscope. And also you can differentiate the different layers by seeing the different color construct of this material. And this materials has lots of application, and this single to few atomic 2D materials are used in transistor. And you know, nowadays transistor has a major contribution in semiconductor technology. So we are using starting from computer or laptop or any smartphone or in calculator, every electronics, there are millions of transistors there. Apart from the transistor, these materials has also applications in solar cells, in sensors like chemical and biosensors, in energy storage devices, and also other applications like photocatalyst and electrocatalyst. So mainly we are working on few of them applications, including transistor, PN junction solar cells, and biosensors. And in the category of transistors, we are mainly working on the phototransistor or photodetector. When you shine light, this light is converted into the electrical energy. And this photodetector has lots of applications in optical communications, including broadband photodetector, infrared detector, in security, different kind of imaging like video imaging, biomedical imaging, motion detection, etc. So now I'm going to my work, and this is the kind of outline of my work. So what we did actually, the intrinsic photoconductivity of few layer MOS2 phototransistor was studied by using multi-terminal method under white light illumination. Then we studied the effect of contact resistance on this optical responsivity, and finally the broadband photoresponsivity, EDCR, and detectivity. So first I would like to start with the MOS2 characterization and device fabrication. So here you can see the optical images and corresponding Raman spectrum of different layered MOS2 flakes that has been exfoliated on 285 nanometer SiSiO2 substrate. And in the right hand side of that Raman spectrum, you can see the optical image of the devices where a few layer MOS2 is used, that is the thickness of 12 nanometer, and the electrodes are fabricated in Argonne National Laboratory, where by using the laser writer, and the metal contacts were used chromium and gold, which are 5 nanometer and 80 nanometer thick. And in the left hand side below, you can see the schematic representation of these devices with the measurement scheme. So from one device, there are two type of measurements we used. One is 2-terminal and is 4-terminal. So 2-terminal measurement was performed using the source and drain contacts, And 4 terminal measurements were performed using source and drain as current measure and injection, and V1 and V2 is used to sense the voltage drop across the channel. And in the right hand side, you can see the electrical characteristic of these devices without no light illuminations. And so figure A and B shows the drain source current as a function of drain source voltage at different backgate voltage in both the 2-terminal and 4-terminal measurements, where you can see both the measurements shows the linear IV characteristics of the devices. And figure C and D basically shows the transport properties of the devices under no light illumination. And from this figure C and D, we calculated the field effect mobility by using these equations. And we find that in 4-terminal measurements, a larger field effect mobility compared to its 2-terminal measurement. And this is due to the effect of contact resistance, because the advantage of using the 4-terminal measurement is we can eliminate the effect of contact resistance here, which is very vital when we are measuring intrinsic photo transport properties. So, and then we study the photoresponse behavior of MS2 device under white light. So figure A and B actually shows the drain source current as a function of voltage at different optical power for both 2-terminal and 4-terminal measurement. And you can see that with increasing optical power, the drain source current is increasing. And for 4-terminal measurement, we found a significant enhanced photocurrent compared to its 2-terminal one. And then we calculated the photoresponsivity using this relation, where R equal to IPH by P optical power. And we plotted the responsivity as a function of backgate voltage at different optical power. But you can clearly see that the responsivity decreases with increasing optical power. But we found a quite higher, that is 3.5 times higher responsivity for 4-terminal measurement compared to its 2-terminal measurement. Then to understand the relation between responsivity with optical power, we plotted responsivity and functions of light intensity, and we fitted this experimental value using this power law, from which you can get the exponent gamma, which is actually indicates the effect of light illuminations on the responsivity. So from the figure, you can see clearly the responsivity is decreases with optical power, and this is due to the trapping of charges at the interface of MOS2 and the semiconducting MOS2 and the metal contacts. So to understand the effect of contact resistance on resist responsivity, first we extracted the contact resistance using these equations, using this relation from the 2-terminal and 4-terminal measurements. Then we plotted contact resistance as a function of backgate voltage, where you can clearly see RC is significantly dependent on backgate voltage, low backgate voltage when the transistor in its off state. And then we fitted this experimental value using this power law, from where also you can get the exponent delta. Again, we plotted RC as a function of P optical power, that is light intensity. And you can see clearly that is RC is not that much dependent on light intensity when there is high backgate voltage. So here also we plotted the experimental value, fitted the experimental value using this power law, from where you can get the exponent nu. So previously we get the relation between responsivity and the P optical power, and now we get the relation between contact resistance and the light intensity. So using these two relation at fixed backgate voltage, you can get directly relation between responsivity and the contact resistance, which is like R proportional to RC to the eta, where eta equal to gamma over nu. So from this relation, you can directly get the eta. Again, you can get the eta from this nu and gamma and nu value using these two relations. So we separately find this and found that these two values are quite matches and equal. So from these things, we can clearly see and find that there is a direct dependency of responsivity on contact resistance, which is an important aspect. So after carefully study the responsivity under white light illumination, we also evaluate the broadband photoconductivity of these transistors in for both 2-terminal and 4-terminal measurements. Here you can see figure A and B. the responsivity as a function of backgate voltage for different wavelength. So in the two terminal case, you can see the responsivity is increases up to 10 volt and then it slowly decreases. Whereas in four terminal case, you can see the responsivity increases up to 40 volt and then it slowly saturates. And this is due to the effect of contact resistance, because in four terminal cases, four terminal measurement, the contact resistance can be eliminated, but that cannot be eliminated in two terminal cases, and there might be effect of heat by which we can see the responsivity is decreases after 10 volt. And also to find the wavelength dependency, we plot photoresponsivity as a function of wavelength and different backgate voltage. And from both the two terminal, four terminal measurements, we see that there is an order of higher magnitude of responsivity is observed in four terminal measurement compared to its terminal one. And this bought peak in the range of 700 to 600 to 700 nanometer is due to the excitonic absorption peak in the MOS2. So when it finally approaches the IR region, that is above the 700 nanometer, you can see from the figures clearly that responsivity sharply decreases in the IR region. And this is due to the very weak absorption of Fulier MOS2 due to its indirect band gap and bandage. And along with this, we also calculated the PDCR, which is photocurrent to dark current ratio, and detectivity, which are the important parameters for the photodetector. And we calculated by using these relations. And we also found that both PDCR and detectivity values are quite higher for four terminal measurement compared to two terminal measurements. And this detectivity value is decreases with increasing, the wavelength, that is in the higher wavelength region. So finally, what we can conclude that intrinsic phototransfer properties can be obtained from 2D material devices by multi-terminal measurements, where you can directly eliminate the effect of contact resistance. So in our MOS2 phototransistor, we demonstrate the intrinsic photoresponsive properties, and we found an order magnitude of higher responsivity compared to its two-terminal measurements. And finally, I would like to acknowledge my mentor, Professor Nihar Pradhan, and all of the co-authors of this work and the funding agencies for this work. And recently, this work has been accepted for publications in Nanoscale Journal. And thank you for your kind attention.
Thank you very much, ma'am. How to manage the interference in this condition? Hello.
Which interference?
Means you have the different channels. In this case, the different channels. So how to manage this interference? If you have the different channel in this connection, then you may have some interference will be appears. I'm not asking about the interface, ma'am. I'm asking about the interference. So how to manage that one?
Interference of what? I mean, the semiconducting channel, because we are using one semiconducting channel, that is MOS2. So I'm not clear what you are asking. Please let me.
In the one channel, you may have the different sub channel, ma'am.
Current? Sorry?
In this one channel, one main channel, then you may have the sub channels, sub band. So if you have the different sub band, so how to manage, ma'am? Ma'am, whenever you creating the different sub band, so you may have some interference, ma'am. One band will be interference with the others, a little bit interference. So managing this noise, it is required to elimination of this noise. So the management of this channel also is highly required.
So you are talking about channel for the light illumination or the channel of that semiconducting?
Professor Sethi, I
Sir.
think your field is not related to her.
Okay, thank you. Thank you.
Actually,
Dear participants, any other questions? No.
Hello.
Thank you, madam.
thank you.
Thank you. Our session is over.
Yeah. Thank you.
Right now, I will welcome Koranakar Nand to this second day of second talk. Professor K.K. Nanda, are you present? Okay, thank you. Thank you. I would like to introduce Professor K.K. Nanda. He did his PhD from the Institute of Physics, Bhubaneswar, India, and right now working as a professor in the Matal Research Center from the Premier Institute of India, that is Indian Institute of Science, Bengaluru, India. He has published more than 200 research papers in different journals of high repute. To his credit, it is interesting to know that he has some patents on white light source using nanostructures. His research interests include synthesis of nanoparticles, nanowires, and carbon nanotubes. One accolade to his credit is that in a recent survey, he has secured a position best research in the world, top 2%. Professor Nanda, please deliver talk. His talk is on resistive sensors. Professor Nanda.
Good morning. So good morning to all of you. So actually my PPT is getting loaded. So it's taking time.
Okay, sir.
So yeah. So first of all, I would like to thank the organizer for giving me opportunity to share some of our results on this resistive sensor. So the title is very short. I use 2 words only. So as you know, the sensor, basically I'll be discussing about the resistive sensor. So first of all, as you know, the sensor is basically a device that measures the physical changes in its environment. And resistive sensor means basically the sensor which exploits the electrical properties, basically the resistance change in the system. So now you can see my slides.
Yes, sir.
Okay. So before so it's not changing. No, okay. So before I go to my presentation, I have some couple of slides about the institute. So basically this institute was conceived in 1896 and established in the year 1909 through an inspired vision of the pioneering industrialist Jamsetji Tata. And it became a deemed university in 1957, and since 1993, it is being funded by MHRD. So we have basically a beautiful campus, which has basically is situated in a 440 acres of area, and it's basically a truly wooded campus with a lot of species of bars and trees. And we have around 3,000 students, around 1,600 MSc PhD students, 900 ME MTech students, and 500 UG students. And we have around 375 academic staff, and they are supported by 125 scientific staffs. And this is basically old data. This year we don't have any visitors, but generally we have 1,000 visitors per year from different part of the world. and basically, the publication is around 1200. So I belong to a research center. That's a material research center. We have around 10 faculties, including 2 emeritus professors, and we have around 60 students, including 10 in PhD students. The objective of our department, as you see here, we synthesize the material, characterize them, then basically evaluate their physical and chemical properties, and for basically to find out the suitability of its application, and finally we go for some prototype devices. So now I come to my talk, and the outline of my talk is basically I give some examples of sensors which relies on the electrical properties. There are temperature sensors, there are pressure sensor, photodetectors, as the previous speaker has already talked about, and also gas sensors. So there are, as you see here, I have listed a few of them. There are various sensors which basically relies on the change in the resistance of the material, okay, or the resistance of the device. And especially we have done some work on SNSE2, thin film for photo detection, then some ammonia sensing using silver, gold, and carbon nanostructures. So I'll give you the introduction and the results which you have done in that field. So in general, so what we know basically, like we have come across the word resistance when we in the class or in the lab. And what we know basically, the resistance, especially of a material, depends on the dimension basically, and which is basically length and area. However, the resistivity is independent of this dimension. So then actually temperature. So if the resistance changes with temperature, of course, you cannot say that it can be used for temperature sensing. There are some criteria have to be satisfied to qualify for the material or the device to be useful for temperature sensing or any sensing. Then gas sensing, basically when the change of the resistance or the resistance changes with environment. Like suppose in oxygen atmosphere, we have some resistance, and in presence of some ammonia or some other analytes, the resistance changes. Okay, so then that can be exploited for gas sensing applications. Similarly, when you shine light or irradiate light, okay, of different wavelength, like the previous speaker already talked about the white light based on MOS2. So basically, if that change in the conductivity, resistivity, resistance, whatever, then it can be exploited for the photo detection. And pressure also, similarly, if you change the pressure of the surroundings, if the resistance changes, then that can be exploited for pressure sensing. So what are our requirements for any sensor? This is in general. So it should be low cost. Hello? It should be low cost. So basically, if I'm talking about some material, the material should be of low cost, and the device can easily be fabricated. That is one of the important issues. And it should be small so that you can put the sensor even in a tiny place. So construction easily duplicated, and it should be stability over time. It should not change with time. So that today suppose the reading is 100 ohm. Tomorrow at the same temperature it should not be 110 ohm. So it should be stable over time. Then there should be accuracy, and also the range is important. Actually, like for our health center, like clinical mercury thermometer, the range is very small. But for our lab requirement, we need wide range sensing. So an important thing is the sensitivity. So for example, suppose if I'm talking about a resistance thermometer, see 1 degree change of the temperature, what is the change in the resistance? So basically dr by dt is the sensitivity and Eg output. How I can measure that output? So for example, as we know, when we measure the resistance, we don't measure the resistance directly. Basically, you have to apply a bias and measure the current, and eventually you get the resistance. So henceforth, if I am showing some results, I may not show the results on resistance, I will show the results on current, basically. Because if you apply a constant bias, you can basically deduce the resistance from using the formula V by I. So it doesn't matter whether I represent my results as R as a function of some parameter or I as a function of that parameter. And another interesting, basically, thing is that the fitting equation. So suppose I have the output, and especially here, I'm talking about the temperature sensor. So basically, if you increase the temperature, the output, what I'm measuring in case of resistive sensor is the resistance, how the resistance is changing with temperature. It is good or is the best basically if the resistance is linear with temperature. I have taken an example of mercury thermometer where actually, as you can see, the height is linear with temperature. So you can basically, what we don't bother is basically what is the height and all. We just see the temperature in the scale. And that's how we get the temperature of our body. So, and especially there, it is the height which is linear. If it is not linear, as I have put in a figure here, the which is going through a zigzag path is not good at all. Okay, because for the different temperature, you have the same output. So it's very difficult to know that. Suppose I have the resistance and that resistance corresponds to different temperature. So I don't know if I know the temperature, say for example, the resistance, I cannot specifically tell that this is the temperature if it is going through a zigzag path. However, it is good or probably the best if it is linear. Might be okay with the lowermost curve. So if you have, say, for example, resistance versus temperature or any pressure, if I am talking about the pressure sensor, the pressure as a function of temperature is linear, that is really good. Otherwise, you have to find a suitable fitting equation to represent it. So that once you know the pressure or resistance, you can find out the temperature. If you have basically you deduce the temperature from some physical parameters. So this is also one of the key aspect of a sensor. So I just give an example. This is used in the lab, basically platinum 100. This is called RTD, basically resistance temperature detectors. It's the most common type of RTD used in industrial applications, and it can be used, say, for example, minus 260 degree to 850 degree centigrade. And the number 100 in the name, say PT 100, that indicates basically a resistance of 100 ohms in 0 degree at 0 degree centigrade. And if you look at, this is the resistance and the temperature curve. As you see, the resistance basically is increasing linearly with temperature. So you can deduce basically the sensitivity. And the sensitivity also is important because, as I have mentioned, that if you change the temperature by 1 degree, what is the change the resistance? If it is 0, so you cannot use it. If it is too high also, there may be a problem in basically, measuring the outputs. So it should not be huge so that for low temperature, you get the current in microampere, and for high temperature, suppose you are getting at, either nanoampere or picoampere. So you have to, that it is not easy to measure the output that easily in a wide range. So its sensitivity basically should not be high, sensitivity should not be also low. So other temperature sensors, diode is also used, thermistor is also used. Basically, thermistor is basically again the resistance temperature detector, the thermocouples. Then there is interesting one called bimetallic stripes. In this case, basically you have two dissimilar metal together, and when the temperature is increased, there will be a bending because the lattice expansion of these two different material will be different, and so it bends as you increase the temperature or reduce the temperature. And basically, that is one of the sensors, the bimetallic stripes, that is used in the in-flight temperature monitoring. And of course, like liquid in glass thermometers, which you use in the clinical application. Like if you go to the health center, they have a mercury thermometer in a glass. So this is basically, scientific terminology is called liquid in glass thermometers. And then we have also luminescent based thermometry. Basically, in this case, the luminescence or if I'm talking about the photoluminescence, the luminescence intensity that changes or that varies with temperature. And that is used as a proof for luminescence-based thermometry. So there are various other thermometers also. Now I'm coming to, this is a simple work which was carried out in our lab. This is a pressure sensing using NCNT. NCNT basically represents that nitrogen doped carbon nanotube. Okay, so nitrogen doped carbon nanotube, why you cannot take carbon nanotube? Because carbon nanotube in principle is ineffective, but once
Ayuda a ଖାଇବ ମତେ ଆଉ ଟିକେ ରଖିଲା ପ୍ଲେଟଟା ଆଣିବା ନା ନା ଫେର କ'ଣ ହେଲା କୁଆଡ଼େ ପଡ଼ିଛି ଇଏ ତ ତାଙ୍କର ପ୍ରୋବ୍ଲେମ୍ ତ ଠିକ୍ ତ ଅଛି
Still ହେଇଯାଇଛି ଭଳିଆ ଲାଗୁଛି
ତାଙ୍କ ପ୍ରୋବ୍ଲେମ୍ ଆମ ହ୍ୟାଙ୍ଗ ହେଇଯାଇଛି
start
Professor.
Hello?
Yes, I think I can hear you, but it might hang, I think.
Tell you here.
Oh, I see. Okay.
Yeah. So, okay, coming back to the work nitrogen doped carbon nanotube. So basically, if you replace one carbon, so let's assume that if you replace one carbon by nitrogen, so then nitrogen being more electron, so it will be negative. It will be negatively charged and carbon will be positively charged. And any oxygen molecule comes in the vicinity of the nitrogen doped carbon nanotube, carbon being more positive compared to, because of the nitrogen in the vicinity, so oxygen becomes slightly negative and prefers to get attached to. In that process, oxygen being more electronegative compared to carbon and nitrogen, so it extracts electron from the nitrogen through carbon. And in that process, the number of conducting electron that gets reduced because this oxygen takes away and becomes O2 minus. And that's how the current basically decreases or the resistance increases. So as you see here, the first curve that is basically represented like IC versus chamber pressure. As you see that if the is decreasing, basically the current is increasing. Basically, when the pressure is decreasing, you are removing oxygen from the surface of the nitrogen carbon nanotube. And when the oxygen gets removed, basically it gives back the electron to the carbon nanotube. So the number of conduction electron increases and the current increases. So when the current is increasing, basically the resistance is decreasing. So just is a kind of, we have plotted. So in this case, the scenario is that the sensitivity, basically the change in the current with respect to the pressure, that is dependent on the percentage of nitrogen doping. So if the percentage of nitrogen doping is high, the sensitivity is high. So that is one of the interesting results from this point of view. And especially we have done this experiment up to 760, mercury pressure. So in that range, what we observe that the current as a function of the pressure is linear. So use that for pressure applications. So now I come to another part or another sensing. So that is basically photodetectors, and generally there are linear devices which is called basically photoconductors, and there are also non-linear devices, photodiodes and all. And in case of linear devices, the current is linear with voltage, and once you shine light of suitable wavelength, I will say that suitable wavelength because the energy should be higher than the band gap of the material. So once you then from the valence band goes to the conduction band, and as we know, the conduction will electricity, and holes in the valence band conduct to the electricity. The electron in the conduction band doesn't conduct to the electricity. So why we need basically study this? Why the photo detectors is required, or why we want to detect the photons? As you see here, we have the limit. A human basically has, the exposure limit, as I have put it in. And our eye is sensitive to basically the visible light. So from especially 370 to 750 nanometers, that our eye is sensitive. Above 750, it is not sensitive. Below 370, also not sensitive. And as you see, the UV light is below like 400 nanometer. And the exposure limit is very low for UVC and UVB. So basically around 300 nanometer and below, our exposure limit is very low. So basically the UV light can cause premature aging, as well as can damage the DNA in the skin, and also can cause the skin cancer. So basically we need to detect, okay? And these are few familiar applications, which is basically, as you see here, this is smoke detectors. In case of smoke detector, we have an LED. So the light basically, the light comes out from the LED, and once there is smoke, that light gets scattered and it falls on the photodiode, current increases, and that there will be some other electronics, and that triggers the electronics, and you get the alarm. Similarly, in the lab, what you use for atomic force microscopy, they are also used for detectors to monitor the profile of the cell. And of course, we are Indian, so we watch cricket a lot, and the umpire use a photodetector basically to measure the light intensity, and the intensity is below a critical level, then they call up the play. So these are the few familiar applications which we come across in a day-to-day life. So I think I'll skip this slide because the previous speaker has already mentioned, but I'd like to mention here, there are different figure of merits like sensitivity, responsivity, transit time, external quantum efficiency and all. But we have done some work which focuses on photocurrent, how one can increase the photocurrent, and how we can increase basically improve the response time. And basically these are the two key parameters for a photodetector. So this is basically, I have already mentioned a part of it, like photodetection using a photoconductor. So basically it's a linear device. when and it's basically connected, source, so that you can apply a bias and measure the current. So when you shine light, the electrons from the valence band goes to the conduction band, and once you apply a bias, they get separated and they are collected at the different electrodes. And especially if it is a linear device, the transit time or the response time, it depends on the length of the two electrodes, as well as the applied bias and the mobility of electron and hole in the semiconductor. So I'll come to that a little bit later. So these are the material aspects of a photodetector for IR sensing. So indium gallium arsenide, germanium, photodiodes, lead sulfide material, lead selenide, indium arsenide, so platinum silicide, indium antimonide. These are the materials actually. If you go through some literature, you'll find these are the materials exploited for IR sensing. Similarly, for photodetectors, the gallium nitride, silicon carbide, zinc sulfide, zinc oxide, as you look at, these are wide bandgap material. And especially if you compare these four, then zinc oxide is one of the best material. So not only, it can be easily synthesized. You take simple zinc and vaporize it, you can get zinc oxide. And you can easily synthesize, basically from the synthesis point of view, zinc oxide is easier and it's also not toxic. However, if you look at the exciton binding energy is 60 MeV, which basically limits the photocurrent. So how it plays a role? So basically the exciton binding energy, basically the binding energy between electron and hole, and if it is higher than that basically room temperature, which is 26 MeV. So if it is below 26 MeV, they will not get easily recombined, but if it is above 25 or 26 MeV, that can easily recombine. So in that case, so zinc oxide, if you look at from the band gap point of view, is 3.2 electron volt. If you look at the synthesis of the metal point of view, it is easy to synthesize. So from that point of view, one can really, we can think of zinc oxide. However, there are a couple of drawbacks. As I have mentioned, one, that's 60 MeV. And this is one of the reasons why if you synthesize zinc oxide, any process, you get some luminescence. Because you get luminescence when electron and hole gets recombined. Similarly, because it's zinc oxide, it's always there is some oxygen deficiency, so they are prone to oxidation. So presence of oxygen can influence the performance. So these two things basically keeps, or basically the drawbacks. Overcome. How if it is suppose I want to use zinc oxide, can I avoid this recombination of electron hole, even though because I cannot influence the binding energy. So is there any means where I can do that? So we have made some effort. So we synthesize zinc oxide by sputtering, and then we basically sprayed carbon nanotube, nitrogen doped carbon nanotube, as you see, towards one electrode. So in that process, what happens? See, in case of, I'll consider that bare zinc oxide. In case of bare zinc oxide, the electron holes get generated when UV light is shine on it. And then when you apply a bias, electron goes towards the positive electrode and holes goes towards the negative electrode. And in between, they get recombined also. However, if you have a coating of nitrogen carbon nanotube, depending on the the band position of zinc oxide and the band position or the Fermi level of nitrogen doped carbon nanotube, electrons or hole can get transformed. So that reduces the recombination. So it provides a conducting path to the electron in our case, and that reduces the chance of recombination, and that's how we get large photocurrent. And this is in one example. So I'll not go into detail. So the photocurrent basically increases with nitrogen doping. So If you increase more nitrogen in carbon nanotube, basically the photocurrent increases. And of course, if you load more and more nitrogen to carbon nanotube, that also increases the photocurrent. So basically, in this case, we are above. You see this when you can elevate the electron conduction, and that conduction electron that gets transferred to CNT or NCNT. So that avoids the recombination in zinc oxide, and that's how we get a huge photocurrent. And this is how, this is a PL spectra of the zinc oxide with and without or presence or absence of NCNT. So the red curve shows the without NCNT, and the black curve shows with NCNT. When you just decorate or coat a part of zinc oxide and measure the photoluminescence nearby, then you can see a drastic change. Basically, especially there is a change in the photoluminescence intensity. That is because some of the electron, okay, already in nitrogen to carbon. So that basically inhibits the recombinations, and so that's why the luminescence intensity goes down. However, if you look at the literature, there are two responses. One is the first response component due to the solid state. Like once you shine light, immediately electron goes to conduction band, and once you switch off the light, the process stops. So that is basically a fast process. However, there is a slow process also associated with zinc oxide, basically zinc oxide based, zinc oxide thin film based devices. There is also, like as I mentioned earlier, that the oxygen adsorption also plays a key role. And that is a slow process. The oxygen adsorption may be a little bit faster, but oxygen desorption may be a faster process, but oxygen adsorption is a slow process. So you may see a fast response, but a slow recovery if there are oxygen, and that influences the photoresponse. However, that is not the case in case of nanowire. This is, as you see, it's a very old report in 2002. It was reported of zinc oxide nanowire as UV detector. So in this case, the response is, really fast. So when I'm talking about response, basically response as well as recovery. That is important. Recovery is also important for a sensing application. You don't have to wait hours together. Okay, you don't have patience to wait hours together. You should be ready for the next use. So if the response time is fast, so we can really think of using that material for application. So in this regard, we have also done some work on SnSe2 based sensing. So we synthesized SnSe2, we spotted SN, and then we selenized SN film, and then film. It was 140 nanometer to 1200 nanometer thick film. And we found that the band gap of this material depends on the thickness of this SnSe2. If it is 140 nanometer, the band gap is around 2 electron volt, whereas if it is 1200 nanometer, it is 1.2 electron volt. So then we exploited for photo detection. As you see, it is a linear devices. We just take top of the film. It is basically chromium gold contact, which gives us. So we tried actually different thickness of this SnSe2 films, and what we observed is that, and as you see, this is IR sensing, the 1064 nanometer. As we are in decreasing the film, especially it shows some photocurrent, but for especially 140 nanometer, it doesn't show. It's very weak. Okay, that is expected because the band gap is around 2.4 electron volt, 2.04 electron volt, and the excitation wavelength is 1064 nanometer. So we don't expect basically, or we're not expecting that 140 nanometer thick film to, give any photocurrent, which is apparent here. Very little with some 0.6 or 0.5 microampere. However, we tried with white light, and it gives good, good response to good photo current. So in this case, what I would like to emphasize is that the response time is typically 2.7, depending on the bias. If it is 5 volt, it's 2 seconds, and if it is 10 volt, it is 2 seconds, and if it is 5 volt, it is 7 seconds. So higher the bias, basically, lower the faster is the response time. Now I come to the photo detection. So using a PN junction, so in case of a linear device that I have mentioned, it depends on separation of the two electrodes. It depends on the mobility. It depends on the electric field. But in case of a nonlinear device or photodiodes, it depends on, again, mobility. It depends on the electric field, and also it depends on the depletion voltage. And if you look at the literature, so you can have always, even if it is a linear device, you can have electrode separation of few micron. In this case also, you can have few micron. Generally, it is few micron in case of a photodetector or a photodiode. So in this case, we don't have to worry too much about the separation of the electrodes. Just you fabricate a diode, and the typical depletion width is in nanometer. So we are expecting, basically, when we started this work, if we have a diode, then the response time will be much faster, because the depletion width is typically in nanometer, and L you can have in micrometer. So keeping that in mind, we again took SnSe2 and deposited basically a layer of PETOT PSS. So SnSe2, what we found out is an N-type material, and a PETOT PSS is a known P-type material. So we fabricated a SnSe2 PETOT PSS based PN diode, and then we studied the photo detection behavior. As you see, it's not a very, what we are expecting earlier, that it can be a really, non-linear IV characteristic. It is so a non-linear IV, not like a perfect diode. You cannot say that it's really a rectifying, diode. But definitely you can see there is some, anisotropy in the current value. By doing so, I'll not go into detail. By doing so, we are able to have a response time of around 1 second, which was earlier, or say, for example, 2 seconds or 7 seconds. Now it is of the order of 1 second. So then we thought, can we increase it further, or we can improve it further? Because the PETOT PSS, in that case also, we found that the mobility is very low. We started with a PN junction, SnSe2N, and PETOT PSS P type. Taken a linear device, SnSe2 PSS has a very low mobility. So because of that, probably we couldn't improve the response time, significantly. So then we thought of taking silicon. So in that scenario, what we did, we took silicon. We took silicon and deposited SnSe2. And then we found that the response time is in millisecond. So what we have actually achieved in this study is that we can improve the response time. Of course, by taking a junction and material of high mobility. So that is our basically conclusion. So we are able to, by taking the silicon and SnSe2 PN junction, of course, we started with P-type silicon and N-type SnSe2. We found out that response. So which is basically, you see, there is a drastic improvement in the response time. Our main target was basically the response time. So we have also done some studies. As I have limited time, I'll just mention nitride. We have done some work also. But in that case, we have taken actually, as you see, the pattern such a way that they are like, you can imagine like 60 degree at all the contact. So we have taken, basically we have filled out orientation dependent found that the mobility depends on the orientation of the film, so and has the photo response. So I'll skip this and I'll spend maybe minutes on some work on sensor. So in this case, basically a chemical sensor is a material that changes its electrical resistance in response to change in the nearby chemical environment. And I'll skip the introduction. I'll come to the interesting part here, or part which is basically required for the presentation. So generally, the metal oxide and especially tin oxide, zinc oxide, that are exploited or used basically sensor. And this works at elevated temperature. It doesn't work. This tin oxide, especially based sensor, doesn't work at room temperature. You need to heat it to around 200 to 300 degrees centigrade. So in this case, as you see, I have taken a R versus resistance curve from a journal called Journal of Applied Physics, as you see here, and tin oxide being an insulator. Okay, we also assume we are also called this a semiconductor because the conductivity actually falls in the range of a semiconductor because there is oxygen deficiency, and that leads to N-type conductivity of for SnO2. And this is the basically resistance per curve of a SnO2 thin film in oxygen atmosphere. That is interesting as you see here. The resistance is decreasing up to 150 degrees centigrade, which is expected because as you increase the temperature, the probability of electron in conduction band increases. And that conduction band electrons basically contribute to the conductivity. So it is expected that as you increase the temperature, in case of a in case of a semiconductor or in the resistance basically the resistance decreases as you increase the temperature. But surprisingly, what is happening here in atmosphere, the resistance is increasing again, like a metal. See, we know that in case of a metal, the resistance increases, and in case of a semiconductor and insulator, the resistance decreases. But it's not that it is going from metallic semiconductor to metallic behavior. It is what is happening when the oxygen is getting absorbed on the surface above 150 degrees centigrade. Before or below 150 degrees centigrade, the oxygen maybe gets Fiji absorbed. But beyond 150 degrees centigrade, the oxygen gets absorbed, and in that process, I have mentioned that at some point of time that oxygen has a tendency to take electron. It is more electronegative. When it takes electron from N-type material, what happens? The number of conduction electron goes down, and that's the reason the resistance increases. And that is basically exploited for gas sensing applications. So your sensor basically keep at 250 degrees centigrade in presence of oxygen. So the resistance is of, for example, 4 into 10 to the power 6 ohm. Now I pass a reducing gas. Suppose I have to detect hydrogen or carbon monoxide or whatever, basically a reducing gas that interacts with the absorbed oxygen and takes away the oxygen, so giving back the electron. So in that process, the resistance drops down, and the change in the resistance will give you the concentration of the analytes. So basically the change in that. So this is the principle of a metal oxide nanostructure is best sensors. And as I have told you, the hydrogen sensor or many sensors of reducing gases, that is basically based on tin oxide. So in that scenario, work especially targeting on room temperature sensing, and here the oxygen adsorption plays a key role. So similarly, can we have a material which can do this process, or the change of the resistance when the oxygen gets adsorbed on the surface of that material? Okay, can we have a material? If you remember, I have mentioned about nitrogen dot carbon nanotube. Nitrogen drop carbon nanotube when oxygen comes close to the material, it becomes slightly negative, and you have N minus and C plus. So oxygen prefers to come or get attached to carbon, which is of course positive. But oxygen being more electronegative, it takes electron from the nitrogen. So that's the how that trigger us to try this nitrogen doped carbon nanotube or carbon nanostructures for gas sensing applications. So we have tried that. So I'll come to that result and complete my talk. So I'll skip this. So what we did, we started with basically a green synthesis route. We started with coffee powder. As you know, it has chicory as well as caffeine, and caffeine basically it has carbon, hydrogen, nitrogen, carbon and nitrogen source. So we took coffee powder, dissolved it, we tried water, and then we hydrothermally treat it at, say, for example, 180 degree, 200 degree centigrade for few hours, like 5 hours to 12 hours. And then in that process, we are able to synthesize nitrogen doped carbon nanoparticle. And by varying the time of the reaction, we are able to basically increase the nitrogen atomic percentage. So actually the target, what we had in mind basically, if we do that, if you increase the nitrogen percentage, the sensitivity should increase, and that's what we have observed here. We have also tried carbon nanoparticle, which is synthesized from sucrose, and nitrogen doped carbon nanoparticle synthesized from. So this is how it happens. 6.5% nitrogen doping. So as you see, carbon nanoparticle also give you some current when the ammonia basically is passed through it. But if you look at the magnitude of the current is 70 here in case of CNP, 120 for 4%, again around 120 for 5%, but around 250 for 6.5%. This tells us that if you increase the doping, then there are a number of active sites increases, and hence the sensitivity also increases. So this is how, but what I put here, all the process happens or the sensing is possible at room temperature. So that's how, if you can start with room temperature application, then you can have this nitrogen doped carbon nanotube or nitrogen doped carbon nanoparticle for the gas sensing applications. So I hope I cover the things actually what I have to cover, but there are some interesting results also. We have done some alcohol sensing based on these carbon nanostructures, which is really interesting, but I don't will. So I'll take some questions if you have. Actually, we have I'll stop.
Thank you, sir, for nice talk on nanomaterials considering semiconductor effects. Now we shall have some brief discussion on this topic, resistive sensors. Please, participants, if you have any questions, you can ask Professor Nanda. Hello, participants, please.
Sir, hello.
Yeah. Yes.
Yes. Actually, just one query.
Yeah.
Some oxygen-related things. So, that means sensor or any kind of material when you are some oxygen deficiency there, or
you are talking about the gas sensing only applicable for hello Can you write down the question? Otherwise,
Professor Mandi, write your question on the chat. Any questions from other participants?
there is some question on oxygen. Hello?
Hello? Hello? Hello? Hello? Hello? Yeah, Dr. Nanda, I think Nilay has given one question in the chat box. You may see in the chat box.
Just is it applicable for piezoelectric materials? Which one you are talking about? Dr. Mahanti. Hello? The oxygen adsorption? Is your question is related to the oxygen adsorption on piezoelectric materials?
Yes.
Yeah. Yes.
Yes, sir. Oh, sir.
Yes. Yeah. So basically, you know, what?
Or all this piezoelectric material which you are
Any oxide which has basically oxygen deficiency, okay. See, oxygen absorption may take place, but if it is physi-absorbed, the oxygen is the electron will not be shared by the oxygen. To high temperature, around 200 to 300 degrees centigrade. As you see from the resistance versus temperature curve, beyond 150 degrees centigrade, the oxygen starts taking electron. Okay.
Okay, sir.
Yes.
Thank you, Professor Nandi. Many thanks, Professor Nanda, for his nice talk on resistive sensors, nanomaterials. Thank you, sir.
Thank
now,
you.
shall I invite third Professor Prasanna Kumar Sahu. Good morning, sir.
Good morning.
Are you, sir?
Yes. Can you hear me?
Okay, thank you, sir.
Is it clear or I need to...
Yes, sir.
Is it clear? Okay. Better I can use my headphone.
Professor Nanda, please.
Hello.
Yeah, I just
take your slide.
Yeah, how to do that?
Dr. Sahu can now present.
But at the same time, Nanda's slide is appearing.
No, that will not appear. If Dr. Sahu will present, then that slide will go.
Can you see my slide?
Okay, sir. Professor Sahu.
Yes. You can see it, right? Okay.
Welcome you to the second day of this webinar on recent advances in science and technology. Dear participants, he is Professor Prasanna Kumar Sahu. He did his PhD from Homeopathy National Institute, Indira Gandhi Center for Advanced Atomic Research, Kalpagaon, Tamil Nadu, India. He did his postdocs from 2 foreign countries, one is from Brazil, from the Institute of Physics, GW, State University of Campinas, Campinas, Sao Paulo, Brazil. Then he did his postdocs from USA, Florida, from the University of South Florida, Department of Physics. He is now working as a assistant professor in Material Research Center, IIT Kharagpur, India. To his credit, he has a good number of research publications in journals of high repute like Advanced Functional Material, Nature Communication, Nanoletters, etc. His research interests include 2D, quantum materials, van der Waals, heterojunctions, excitants, polaritons, age effects, growth of multi-junction lateral and vertical heterostructure of 2D large materials, nanoscale physics, optoelectronic device characterizations. Now, he will deliver his talk on this subject, emerging low-dimensional materials. Professor Shah, please start.
Yes. Yeah, thank you for the invitation and for the kind introduction. So today I am going to talk about emerging low-dimensional materials. Especially, I will focus on the two-dimensional material, which is now recently a very emerging topic. It have many fascinating physics and many interesting properties that one cannot see in their ball counterpart. With this, I will talk about what are the challenges in this field and what are the new prospects in future and development of quantum technology. Okay. Why this slide is not moving? Yes. So now we all are fascinated for very flexible electronics, that we want electronics to be flexible and it should have high performance. That means you don't want to charge for a long time and you want to compute or send a message in a fraction of a second. That means it should be high performance, it should be transparent, it will be now new fashion, and also in that, and also we need ultra thin body. That means it should have very thin structure that our device size will be compatible and we can carry or fold it, and a whole computer, if you imagine whole computer, you can fold it into your bag or in your pocket. That's the idea of the future semiconductor technology. And also flexible materials, especially ETA2, the wearable electronics, smart watches, smart glasses, all are the fascinating things going on in this field of science, where low-dimensional material, nanomaterials, two-dimensional materials can play a bigger role in order to achieve these objectives for real-time application. Okay, another thing you can figure out, whole world is now full of Wi-Fi signal, right? So whether the Wi-Fi signal is also electric field, electromagnetic field, whether we can harvest that energy and we can charge our more in like small devices, including mobile, smartphones, all things. This can be a very good thing that we don't need to charge ourselves cell phone, because everywhere you go around the world, you can find, or in the cities, you can find Wi-Fi signal, so it can self-charge itself. And for that, one way, the Thomas Valikas group from MIT, they developed this two-dimensional material from metallic to a semiconductor type. From that, they can able to harvest, you can convert the Wi-Fi band of radiation into a DC current, so that it can empower or power your device. But still, it is in the research stage. It is a long way to go, because we need to not only just one proof of principle based device, we need an array of devices so that we can harvest enough energy from the Wi-Fi signal. Not only that, if in a bigger objective, you think about the Swiss long-range experiment on solar power aircraft. Right? You can think, if you compare to your typical Boeing airplanes, that is, you can see its weight is around 300 tons. That can carry people more than 500 people, or along with the other accessories. But as a proof of principle, they try to run these these solar aircraft, and that we can think about, these have 17,000 solar cells. and it's only 4 meter long propellers, all these. But the bigger challenge is it cannot go for long, and your average speed is just 70 kilometer per hour. This is not be viable. So that is any typical car or you drive through this more than this velocity on the so that what will be more challenging if we can develop a lightweight material, because the presently whatever the conventional solar cell, that take itself is more weightage to the system. If you develop or you discover new kind of ultra thin material, and that can do the same job or even better job as compared to your conventional semiconductor, that can be useful for developing such low cost and also high efficient solar power aircraft. So what we need a new generation of solar cell materials that should be lightweight and should be high efficient. And so how we can develop such sustainable and smart and efficient future technology? One guy is asking, then you can say that, so I will use 2D materials, the new kind class of materials which is recently developing in the last couple of years. So that, and their heterostructure like graphene, which got Nobel Prize, is a single atomic layer of carbon, and also beyond. And we will see in subsequent slide why the world need another family of graphene. Not graphene is why it is not self-sufficient. So that we'll talk about today. We'll discuss more on this class of materials that is called two-dimensional material. So why size matter? It's from because I can see this there like audience from very different wide range of different backgrounds. So that's what I will talk in more general sense so that it will touch to everybody. So in general, if you say three-dimensional material, the density of state, that means with energy, that means how the electron occupy inside the energy state is occupied. The energy, that means how the electrons are occupied in the materials. So it is more like continuous like that. Order of to the power half. So if you go to two-dimensional material, that means you are restricting the electron motion from three dimensions so that your electron can only move to x and y plane. So you are restricting one direction, like you can say from this side, so that your density of state is more like stepwise, step-like function. So that means a particular, and for a particular band of energy, the number of states are constant. If you go for one dimension, that means you are restricting the electron motion in two dimensions, so the electron can move only one direction. What is the purpose is if you three dimension, the electron can move all possible way. That's why they can hit each other, and because of the resistance, so then it creates drift velocity is less and all. And for if moment you can control the motion of the electron, that will be more useful to selectively develop specific devices. Like you can selectively access particular bands or particular states so that it can be useful for many unique applications like quantum computing, like quantum LED, or this kind of you can manipulate single states. That's what the need necessary for developing quantum technology. So more focus will be here in this two-dimensional material where you can make large scale electronics, because because it's a flat plane, you can say it's a 2D plane, flat land, and you are thinning down your material to very 0.6 nanometer thick substrates. We'll show that. So what is especially for layman term, what is 2D materials? If you take example of potatoes, like what we eat, you love Bengalis and Odia people love potatoes to put everywhere. So potatoes, if you want to make slice, then what you have to do, you have to cut into small pieces. You need literally a slice for that. That means the bonding between, if you go to zoom into the microscopic or atomic scale level, what you can find, the atoms are literally connected, and you need to break a particular bond, then you literally have to force, right? You put a lot of energy, and the bond may not break in the way you want, but bond will break give away the energy minimum states are there. But if you take a onion piece, like onion like substrate, is what you know is like you peel off layer by